In this video, 7.7, the trapezoidal rule, we're going to introduce the trapezoidal rule approximation and investigate how it improves upon our previous methods. Up to this point, we've seen three distinct methods, really. We started with the left and right endpoint approximations and came up with a more accurate approach through the midpoint rule. And if you think about the midpoint rule as reducing the original interval, the original integral to an approximation using constant functions, you can think about in each subinterval, which we'll call x sub I minus 1 x sub I, we replace f of x, which depends on the specific x in that interval, right? So it could be very curvy, it could be relatively flat, it could be only going up, only going down, etc. With the constant value f of x sub I bar. So the specific, so for instance, let's say this is the function in that interval, just for the sake of clarity. Let's just illustrate what that would look like. Now we're saying we're replacing it with the function value at this point. So instead of the whatever intricacies the original function has, we're approximating it by just a straight line by taking the function value at the midpoint, where this is the midpoint. And that's what the midpoint rule does. Well, we can do better. What if, instead, we approximate this function f with a straight line, not necessarily flat across the way, like it could have a positive or negative slope, between each function value point at the subinterval nodes. So at each x sub I, f of x sub I. And what that would look like instead of taking the midpoint, we would look at the endpoints again, and then we would just draw a straight line through them. And you can see how that might be a better approximation than just taking a flat curve all the way across. So now let's get into the approximation. And it'll be clear in a second why it's called the trapezoidal rule. So we're going to fix the number of subdivisions, n, again. And for each subinterval, we're going to take a special geometric construction here. We're going to find the area of the trapezoid. So remember, a trapezoid, what it really looks like is it's a four-sided closed shape with straight lines, and it has two parallel sides opposite each other, and then the other sides may not be. In this case, we're going to take a trapezoid where we actually have two right angles. You'll see in a second. Formed by the points x sub I minus 1, 0. So on the along the x-axis, x sub I minus 1 comma f of x sub I minus 1. So the function value at the first midpoint. So this is corner of the base. This is the first function value, so first f of x. The next one is x sub I f of x sub I, which is the second function value. And lastly, x sub I comma 0. And that gives us the second corner of the base. Here's what that looks like. I'm going to do a very simple illustration here where you only see two subintervals. So here's A, here's X, here's B. Let's suppose that the curve looks something like this. So if we split up our interval to two subintervals, the actual integral is the area underneath the two. So the area underneath the curve in the first segment, so part 1 and part 2. You actually compute those integrals separately and put them together. That's the full integral. What we do here instead is we take the first corner of the base, x sub I minus 1, 0, in this case the first point, then the function value there, then the function value at the next point, separating the subintervals, and then the point on the base. So you end up getting this shape. Remember, you connect all these lines with, all these points with straight lines. So you end up getting this trapezoid that has this like rectangular base, but the line connecting the first f of x and the second f of x points, those are giving you the trapezoidal shape. And similarly for the remaining subinterval. So each subinterval gets a new trapezoid, and if you put this together, that is, for each subinterval, we're saying that the integral from x sub I to from x sub I minus 1 to x sub I of f of x is being approximated by the area of the trapezoid. So what does the area of a trapezoid look like? So it's the base of that trapezoid divided by 2 times the first height plus the second height. I guess I should call these also h sub I comma 1 plus h sub I comma 2, because they're two different bases. And really what we're saying here is the base is the base length of that trapezoid, which is delta x, right? By definition, that's how we set up these subintervals. This is delta x. This is f of x sub I minus 1, and this is f of x sub I. So really, we're adding up these things. So when we add them all up, we get the approximation, the trapezoidal rule approximation. Is, we denote it capital T sub n. So notice what happens when you add these up, right? So every point that is not A or B gets counted twice, right? So this line, including the 2 points, is shared by the first subinterval and the second subinterval. And that's where you'll see an interesting factor of 2 appear here. So this actually is delta x over 2 times f of a plus, 2 times the sum from I equals 1 to n minus 1 of f of x sub I plus f of b. And then if you write that out long ways, all that means is all the middle function values get a factor of 2 out front. So that's f of a plus 2 f of x sub 1 plus 2 f of x sub 2, and so on until you get to 2 f of x sub n minus 1 plus f of b. And that's it. That's your approximation. So it's not actually that complicated. It's not that much complicated. And as we'll see, they pay off as pretty great because it does improve on the midpoint rule quite a bit. Let's illustrate this example with an example. So once again, we're going to approximate the integral from 1 to 2 of dx over x squared. This time we're going to use the trapezoidal rule using 5 subintervals. And then we'll calculate the error as well. So here, we already had the function values. You can go ahead and go back to a previous video to write down the function values. So our x sub i's are 1, 1.2, 1.4, 1.6, 1.8, 2, or you can do it all over again, it doesn't matter. This was 1, 0.6944, 0.5102, 0.3906, 0.3086, and then 0.25. Okay. Then our t sub 5 is delta x over 2 times f of 1 plus 2 f of 1.2 plus 2 f of 1.4 plus 2 times f of 1.6 plus 2 times f of 1.8 plus f of 2. And that's approximately, remember, delta x is 0.2, that's approximately 0.5058. Wow. I mean, that's significant improvement, really. So, remember that. Call the actual integral value is 0.5, which means our error here, our error in the trapezoidal rule approximation, is I minus our new approximation, right, the trapezoidal rule, which is negative 0.0058. That's really small. Not super tiny, but consider that we only used 5 subintervals. So we could really improve this pretty quickly by taking even 10 or 20 subintervals. So now that we've seen one of these in action, and compared it to what we were working with before, let's talk about the error bound for this approximation. So like with the midpoint rule, we have an upper bound on the largest possible error that can be produced by this method given that you have some interesting conditions that, for all the functions that we're working with, it's not going to be a problem. But so if we know that the second derivative of f is the absolute value of it is no greater than k for all for all x values in between a and b, or this means for all numbers between a and b inclusive, then we can guarantee that the error using this trapezoidal rule approximation as a function of the number of subintervals that we've chosen is no greater than, or the absolute value of it is no greater than, k times b minus a cubed over 12n squared. Compare that to the formula we had for the midpoint rule. So this error bound is not as strict as the midpoint rule, and that's just because we have a well, the reasons for it are beyond the scope of this course, but they are on the same order, so they're both on the order of, sorry, that's a theta, not an O. So in big O notation, that's in the order of n squared. But our error bound is greater than the error bound for the midpoint rule. So it seems like we're not improving, but for practical purposes, usually these are at least as good as each other. This one is even just, I guess, computationally less complex because you're using the function values that were given to you. Okay. So as an example of how we can use this information, what we're going to do is we're going to use the trapezoidal rule to estimate an integral that we don't know. We're going to estimate the integral from 0 to 1 of e to the negative x squared dx, and we will find a maximum error bound for the approximation when n equals 10. Okay, so if we're actually performing this estimation, this approximation, then what we're saying is this integral, which we have no way of finding analytically, we're going to approximate using t sub 10, okay, which is delta x over 2, and delta x is going to be the b minus a over n, in this case 1 minus 0 divided by 10, times the first function value f of 0 plus 2 times the sum from I equals 1 to 9 of f of x sub I plus f of 1, and we're going to skip all the horrible, excruciating details. You can use any calculator that you have available to you. The 0.1 divided by 2 times e to the negative 0 squared plus 2 times, and then this would be, a long sequence of numbers, e to the negative 0.1 squared plus e to the negative 0.2 squared and so on. So you get to plus e to the negative 0.9 squared. Remember that 0. So the way that this order works is in the argument for that exponential expression, you're going to square the x sub i's first and then make them negative. Otherwise, your calculator will get confused. And then plus e to the negative 1 squared. Yeah, so the negatives there, right, they matter. So make sure that you're not losing track of those. And this is approximately, you can take a minute here, pause, and actually calculate that if you want. But the actual value that I've calculated is something along the lines of 0.7462. And you'll be asked to get, a specific accuracy, precision with your estimate. The standard might be anywhere from 4 digits of accuracy to 6, maybe even greater. But okay, so this is our estimate. And now the question really is, what is the maximum error bound for this? Like, how far away is this possibly from the actual value? And to do that, to estimate the maximum value of this error, we need to use that theorem, right, where we find the capital K that bounds the second derivative. We know what B is, we know what A is, we know what N is, so that's not a problem. So we need to find an upper bound for the absolute value of f double prime of x. Oops, sorry, I didn't mean to put a double bar there. On the interval 0 to 1. And I just want to note, this is guaranteed for the functions that we work with using redundant assumptions of continuity, differentiability, blah, blah, blah. Okay? If this were not possible, we could not apply this theorem. But again, for the elementary functions that we use, not all of them, but the ones that we're going to see in this class at least, this is always going to be guaranteed. Okay, so that is, we need to find the absolute extreme values of f double prime over that interval. Back to Calc 1, right? So our f is e to the negative x squared. Then f prime, well, this is the chain rule, right? So I'm going to put the derivative of the inner function in front because it'll make it easier for us to work with the later derivatives, okay? So here we go, right? So f prime is derivative of the inside, negative 2x, times derivative of the outside, which is just e to the negative x squared. Not bad. So that involved chain rule. We would need to do that again, plus use product rule. Call this u, call this v, in order to get f double prime. So f double prime of x is, remember, u prime times v. So, well, is that how I wrote it? No. U times v prime. It doesn't really matter. The order doesn't matter with the product rule. So, u times v prime, which v prime is f prime. So, we get negative 2x squared e to the negative x squared plus, and now u prime times v, so negative 2 e to the negative x squared. And then if we simplify that, pull out the e to the negative x squared, we actually end up with 4x squared minus 2 e to the negative x squared. Okay, so if you were unsure how we did all that, remember we just used the product rule. So if you're unclear about all this, I suggest you go back to chapter 3 and review some of that. But all right, so if we want to find where this f double prime attains a maximum value, or an extreme value, I should say, then we're going to need to solve f triple prime of c equals 0. So f double prime attains extrema where f triple prime of c equals 0. So we need to find the third derivative. Yes, we're going to do this again. So now this is our u again, this is our v. So f triple prime of c equals 0. Well, derivative of u is, what's that? No, sorry, we're going to do u times v prime. So u times v prime here is going to look like negative 2c. I'm using c here just to be clear that, we're looking for a specific value in that interval, times 4c squared minus 2 times e to the negative c squared. Now, u prime times v, so plus 8c times e to the negative c squared equals 0. Okay. Now, if you factor out e to the negative c squared, that can never equal 0, so that's just going to go away. So we actually just end up with, you can distribute the negative 2c into that first set of, basically do the first polynomial multiplication here. Negative 8c cubed plus 2c plus 8c equals 0, which is the same as negative 8c cubed plus 10c equals 0. Factor out a c, you get, and divide by negative 2. C times 4c squared minus 5 equals 0. Then that means c equals 0, or plus or minus square root of 5 over 2. Okay, and then we should also check the boundary conditions. So also check x equals 0, x equals 1. Now, x equals 0 is taken care of. We had that. But we should plug in 1 as well to see which one is actually which function value of f double prime is actually the highest. So now we check. So first, f double prime of 0. And we can go back to this original statement, right? So this one is the actual function that we're interested in, right? So plug in 0 to that, and we end up with negative 2. Okay, so absolute value of that is going to be 2. As for root 5 over 2, if you plug that in, you can pause here and check that what I'm doing here is correct. That's 3e to the negative 5 over 4, which roughly means the absolute value of that is on the order of 0.8595. And f double prime of 1, if you plug in 1, you get 2 to the e negative 1, which means that absolute value is close to 0.7357. Okay. The largest one of these is 2, which means k is 2 for the interval 0, 1. Okay. This was our winner. And then now we can set up the error bound. So the error from the trapezoidal rule approximation, given n equals 10, is no greater than, remember it's k times b minus a cubed over 12n squared. This is 2 times 1 minus 0 cubed over 12 times 100. And this is on the order of, well, 1 minus 0, that just turns into 1, so it doesn't matter. And then 2 and the 12 simplify to 1 and 6. So you get 1 over 600. And that's approximately, that's approximately our error bound. And if you want to get a precise value on this, it has a decimal number. That's about 0.00167, roughly. So our estimate that we found in this part is no more than this amount away from the true value, which is pretty good. Not bad. All right, so in the next video, we cover Simpson's rule, which is the last method that we discuss in this